Okay, we'll start with a few observations or announcements of some Hamiltonicity results, and more importantly, conjectures. And then I'll prove one substantial theorem, which is, I think, the only nice theorem about Hamilton cycles that I know of, except for the two simple ones that I showed you last time. So here are some conjectures. Remember this observation that if we have a bipartite graph with one side bigger than the other side, say a complete bipartite graph KL with L bigger than K, then we can't have a Hamilton cycle because any cycle has to shuttle back and forth and it can't cover all the vertices if the classes have different sizes. So let's generalize that a little bit and say that G, given some positive number, integer usually, but never mind, call a graph G T robust if for every set of vertices that we might delete, there are no more than order of S, so the number of those vertices that we deleted, divided by T components in G minus S. Right, so if T is 1, then we have the requirement that no set of vertices leaves on deleting that set more components than it has vertices, which is exactly the situation. So if that is violated, if deleting this set leaves more components than this set has elements, has vertices, then we can't have a Hamilton cycle, clearly not. Right? Because we have to visit each component, and to get from one component to the next component, we have to go via S. So just like here, getting from one vertex to another vertex, we have to go via the left-hand side. So we clearly need at least as many components in G minus S as S has vertices. And if we allow T to be bigger, then this assumption gets stronger. So we have fewer components, say if T is 2, then we're only allowing half as many components and the rest as S has vertices, and so on. And there's a conjecture, and that's the robustness conjecture. That there exists a T such that every T robust graph has a Hamilton cycle. Okay, so that this is sufficient if we just make this ratio big enough and small enough, and that is open. This was conjectured by Chvátal in, I think, 1970s or something around then. And I think he initially thought it might be true for T equals 2, and that was then later disproved. But nobody knows whether it's true for any T bigger than 2. So that's the robustness conjecture. And this is a sort of natural condition. It's a nice conjecture, I think. Yeah. That was one. Then there's another one, another conjecture, and that has a theorem and a conjecture, and that has a history. It starts with a false conjecture. So the false conjecture says that, or it's a question, whether every cubic, three-connected planar graph has a Hamilton cycle. So cubic, three-connected planar graph has a Hamilton cycle. So if you have a three separator in a planar graph, then you can't have three components. You have fewer than three components when you delete that, because otherwise you'd have a K33 minor. So yeah, it's sort of not totally unrelated to robustness. Planar graphs have some sort of natural robustness as well. Deleting small sets doesn't leave too many components. And so the question was, once more, whether every planar three-connected cubic graph has a Hamilton cycle. And why those properties? Because it was known, and it's not hard to show, that this would have implied the four-color conjecture at the time. So everybody wanted to prove the four-color conjecture, and that appeared to be a way of doing that. And then Tutte, same Tutte as always. I think there's only one Tutte. Disproved that. And he found a counterexample to this conjecture which I just mentioned, but he proved a weakening, and that is in 1956, every four-connected planar graph has a Hamilton cycle. Right, you don't need anything like cubic now, just four connected, so degrees are obviously at least four, but that's all you need to assume. And then we do have a Hamilton cycle, and that's a nice theorem. Yeah, that no longer implies the four-color conjecture or theorem, but it is a nice positive result. Now, my conjecture same for Hamilton circles. In locally finite graphs. Right, remember circles? I showed you what circles are in mod G. So you have G plus all the ends with a nice topology. And then you have these circles, like we have the three-way ladder with three ends, and it went through those three. And we also had the wild circle, binary tree, and then some horizontal additional edges, and that these additional edges made those double rays into one huge circle that contained all the continuum many ends, the wild circle. And so, as I think I mentioned at the time, we don't know of any reasonable, interesting theorem about cycles in finite graphs that doesn't have an equivalent in locally finite graphs for circles. So they're all true or unknown, but none has been disproved. And this is apparently a hard one. There's a partial result due to Henning Brun, who was my student early, and Xingxing Liu, and they proved, I think, this conjecture for 6 connected planar graphs with, there's some bound on the number of ends, I can't remember, something like that. Okay. Then next theorem, Fleischner can't remember when that was. That's 10, 3, 1. Let me see if I made a note of when that was. Yes, 1974, just around the same time. He proved that for every two-connected G, the square has a Hamilton cycle. Right, what's the square? The graph G plus any edges that join vertices at distance exactly 2. Right? So you have some graph G, and then in addition, you join, for example, these two vertices. Those two vertices are already joined, so there's nothing you need to do there. Those two are also going to be joined because their distance is 2 here. Right. So that's the square of a graph. And Fleischner proved that assuming only that G is 2 connected, which that implies that the square has a Hamilton cycle. And that's sort of held the record for having the longest proof. So the original proof is something like over 20 pages, I think. There are shorter proofs now. Yeah. And Achelos Georgakopoulos, my student, so when was that? 2009. Same for locally finite graphs. So Hamilton circles exist in the square of any locally finite two-connected graph. And that has a nice history, that thing. So Achelos came from Athens to do a PhD and seemed quite clever. I didn't know at the time just how clever he was. He is really, really good. But never mind. So there was Achelos, and I set him that problem, and I didn't know myself whether it was hard or not. And I thought it might be a nice thing to try. And so he worked on that for, I don't know, a year or something. And then I had to get really stern with him and say, sorry, but you want to finish a PhD in 3 years or something, so please stop working on that problem. Do something else. And we discussed something else. And so he duly sort of worked on something else and proved some nice things. And secretly, he continued to think about that problem. Then after another year, or 2 more years or something, I can't remember, towards the end of his PhD, and then said, oh, by the way, I proved that. So this is really, really remarkable. It's the strongest theorem that exists about Hamilton circles, or about circles, I should say, in locally finite graphs. Just think what it means. A Hamilton circle is in graph plus ends with the obvious topology that I showed you, a circle that contains all the vertices. A circle is a homeomorphic copy of S1, of the unit circle in the complex plane. So that's a compact set. So a circle in this graph is compact, and compact subsets of Hausdorff spaces are closed in that space. So it's a closed subset. This this circle must be a closed subset of the graph plus ends. And if it goes through all the vertices, it must go through all the ends, because in every neighborhood of an end, you have lots and lots of vertices. Remember, the only neighborhoods of ends, or the basic neighborhoods of ends, were those where you delete a vertex, then you look at a component in which this end lives, in the sense that all its rays end up in that component. And that whole component, with all its vertices and sort of some half edges, that's an open set. These are the basic open sets. And so a circle that contains all the vertices, by virtue of being closed in mod G, has to contain all the ends. Right, but this wild circle graph that I showed you, that is already too connected. Its square is even more, it's even too connected, right? So definitely that must have a Hamilton circle, and the wild circle indeed is one. But in general, as soon as the graph has continue many ends, any positive solution to this must produce a circle that goes through all these ends, continue many ends. So they're all wild. As soon as the graph has enough ends, the Hamilton circles that are required here for this to be true are going to be wild circles. They have to have continue many ends, and, well, they contain a set that is order isomorphic, a set of ends that's order isomorphic to the rationals, or a set of double rays that's order isomorphic to the rationals. It might sort of not actually be isomorphic to the wild circle, but it contains something like a wild arc. Okay, so that's a brilliant theorem. That's really, really nice. That's open. For another year, maybe? Okay. So, that's it for announcements of conjectures and background theorems. And now I want to prove something. Any questions about all this? No. Then let's get going. Let me make a definition first. Call an integer sequence A1 up to AN a Hamiltonian if every graph G with a degree sequence. What's the degree sequence? You just list all the degrees in ascending order, all the vertex degrees. If the graph has n vertices, all graphs have n vertices, meta theorem, that'll be a sequence of integers too, an ascending sequence of integers. So the degrees, and if this degree sequence satisfies, now I nearly got that right, but only nearly, satisfies this. So if that's pointwise bigger than the given sequence, then this graph must have a Hamilton cycle. If every graph with a degree sequence pointwise bigger than the given sequence has a Hamilton cycle. Right? So important, this is not a definition about graphs. It's a definition of a property of integer sequences. And what is the property? The property is that if you come and show me a graph whose degree sequence is at least that particular sequence, then that graph will have a Hamilton cycle. Right? But an integer sequence that's not Hamiltonian will fail to be Hamiltonian as soon as there exists one graph whose degrees are big enough that doesn't have a Hamilton cycle. It doesn't need to fail for all graphs or many or something. Okay? Questions about the, yeah?
And you said the degree sequence is always going up, like
Yes, it's all the degrees listed in ascending order. So the degree sequence is unique. If you have, the sequence of vertices is not unique. So if you have vertices of the same degree, you can list one or the other first. But the degrees themselves, the lower degrees come before the bigger degrees. Yeah?
okay. But like there could be multiple graphs with the same degree sequence, right?
Oh, yeah. Many graphs with the same degree sequence, yeah. Mm-hmm. Okay. Right, so that's the definition. And the theorem, this is again by Chvátal. There's an accent somewhere. 1972. Golly. And that says that such a sequence right, ascending sequence like there is Hamiltonian if and only if the following is true. For every I less than half n, the following must hold. And now something really sort of strange at first sight. If ai is at most I, then a n minus I towards the end of the sequence is at least n minus I. So that looks weird because we're somehow confusing degrees like these are thresholds, benchmarks for the degrees that a graph has to have at least. We're confusing them with the position in which they come. Right, so if a graph has lots of leaves, the degree sequence has lots of ones, and then you can look at the fifth leaf, and you say, oh yeah, the fifth entry in my sequence is 1, which is small, at most 5. Brilliant. So that I satisfies that. Yeah, but why compare entries of the sequence with the position of the entry? It's slightly weird. But here's something that is maybe not so weird. If you look at it qualitatively, what does this say? This says that for many, think of I as sort of not too small. So if AI is at most I, then all the A's before it in the sequence are also at most I, because it's an ascending sequence, right? So this condition says that, yeah, there are many, at least I, vertices of relatively low degree, namely at most I, if this is a degree sequence, right? There are many small values, there are many small little a's. And if you have that, if you have many small degrees and you want a Hamilton cycle, well, it's a good idea to compensate for that somehow. And this compensates for it. It says that there are also many large degrees. So if I is big and you have many of these degrees at most I, then you also, then this is small, so you have many at the end, whose degrees are big, relatively big. Right? Yeah. And it's also, of course, interesting that this is the same I, but notice that how many entries are there starting with n minus I? How many entries are there up to I? Well, I many. Right? How many entries are there that compensate for these I small entries? N minus I, sorry, I plus 1, many. So if you count from n minus I all the way up to n, you have I plus 1 things to count, right? If you count from n minus 1 to n, then you have 2 things. And if you count from n minus I to n, then you have not I, but I plus 1 things. And that will be important later. Okay. And of course, the big thing is that it's if and only if. But it's an if and only statement, not about graphs. It doesn't give us a necessary and sufficient condition for a given graph to be Hamiltonian, to have a Hamilton cycle, but a necessary and sufficient condition for a sequence of integers such that all graphs with degrees at least that big pointwise have a Hamilton cycle. Yeah. So, questions about the theorem, the statement? And if not, then I'll prove it. Okay, proof. So, let's prove the backwards implication first. So, for a given sequence, given A1, AN, assume that this holds, but there's no Hamilton cycle in the graph. The graph will be called G, probably. Okay, so we want to show that given any sequence, if this funding condition is satisfied for every I, this must hold, this implication must hold. If that is true, then, in any graph that satisfies that, then in that graph there must be a Hamilton cycle. So once more. The backwards implication says that if a given sequence satisfies this, then this given sequence is Hamiltonian. What does that mean? It means that any graph with degrees, at least pointwise, this sequence must have a Hamilton cycle. So to prove that, we say we want to show that any graph with degrees at least that big has Hamilton cycle. So suppose not. Suppose there's a graph G with degrees di at least ai, but there's no Hamilton cycle in G. Okay. First thing to notice is that the di satisfy that same implication too. So if you write little d's here, that's going to be true just on the strength of the di being bigger than the ai, and the ai satisfying that. So why is that? Well, that's easy. If you have a di, then we must show that if di is at most I, then dn minus I is at least n minus I. Well, but if di is at least is at most I, then ai is even smaller. ai is smaller than di, right? Then ai is certainly at most I. And then the condition says that n minus I is big, but dn I minus 1 I is even bigger. So the condition clearly is clearly passed on to the actual degree sequence of our graph G, if that's pointwise at least the given sequence. Okay. Now, assume that G has as many edges as possible. With all that we've said before. Right? We take this counterexample here, this G with as many edges as possible. Then look at non-adjacent vertices x and y with largest possible degree sum. Right, so they're going to be non-adjacent x and y in G, otherwise there's a Hamilton cycle. So let's choose, in this particular G with as many edges as possible, let's choose non-adjacent, or pick non-adjacent x, y, so that their degree sum, just those two vertices, is as big as possible. You'll see later why. Then G plus xy plus this edge has a Hamilton cycle. Y, well, it has one more edge. We just have to check that the degree sum, that the degrees of the augmented graph with the additional edge still satisfy that condition, which is sort of very plausible. If you add an edge, then all the degrees go up. Oh, well, some degrees go up and others stay the same. So if the degrees are large, pointwise, here bigger than the AI, then surely after making two of them bigger, they're not going to drop below the corresponding AI. If you do that formally, you have to fiddle a little bit because you have your vertices listed by degrees, and then to this vertex you add, that's x, say, and you increase its degree by 1. Then this little x, or this degree, shifts up in the sequence, possibly. So, and pushes all these others down. So we have to, but then the new sequence with this one bigger and moved up is at least pointwise as big as the old sequence, because those that are shifted down, they're sort of bigger than their predecessors, or no smaller, because the sequence was increasing. So if the predecessors were bigger than the AIs, then those shifted down are still bigger than the AIs. And this thing that moved up just because we increased its degree by 1, its value by 1, that will also be bigger than the thing it replaces, because otherwise we wouldn't have put it there. We put it there, because it has degree bigger than the thing it pushed down. Okay, so it's really true that when we add this edge, by the maximality of the size of G, of the number of edges of G, we do have a Hamilton cycle. So G contains a Hamilton path. From x to y. Right? Because that's the edge xy. With the edge xy, there's a Hamilton cycle. Just ignore the edge and just look at what remains in G. And that's still a path from x to y that uses all the vertices. Okay, so let's call that x1. Then that'll be xn, and x1, x2, and so on. Okay, and now we play the Dirac game. So make a vertex green, put it in I, if its successor is adjacent to x. So I is the set of all indices little I such that xi plus 1 is an edge, and similarly j is the set of all indices j such that xj y is an edge. Okay. And this cannot happen by assumption. Right? So we can't have the same pigeonhole containing two pigeons, because then we'd have a Hamilton cycle. We'd have a cycle with all these vertices. These are all the vertices, so that would be a Hamilton cycle, and we're assuming that there's no Hamilton cycle in G. Okay. So since there's no Hamilton cycle in G, we have A intersect G empty, and that tells us something. So I and j are both subsets of the set of indices from 1 to n minus 1. The last vertex xn is not a neighbor of xn, it's not a neighbor of y, so it can't be in here, and it's also not the predecessor of a neighbor of x, so it's not an I either. So the last vertex here, y or xn, is in neither of those two sets, so both these two sets, they're disjoint subsets of 1 to n minus 1. Okay. Assume, let's give the degree of x a name and assume that x has degree at most degree of y. So they're just two vertices and one of them will have bigger degree than the other, or they're equal. So, and let's call the degree of x h and assume that this is at most y. Okay, so now let's look at the position of x in the degree sequence. so we have 1, 2, 3, n. These are just the position numbers. X is somewhere, and what's the degree of X? Well, I just gave it a name, it's H. Okay, then I claim that I is in this segment. So X itself is certainly an I, because X is a predecessor of its neighbor X1, and maybe not all of them are in I, but I claim that all the xi, all the xi, those where x is adjacent to I minus xi, I minus 1, all these xi, I claim that they're in this segment here. So what does that mean? That I claim that their degrees are at most h. So will log x should be, I marked x, I put x last amongst all the vertices that have degree h. So why is that? Why do the green vertices, these xi, have degree at most h? I see one smile. So do you know the answer? No. Yes? Have you read it? No. No? Okay, go ahead.
Because they're not adjacent to y and some of the degrees.
Brilliant. Yeah. Wow. Okay, so these little xi's, these little i's are not in J. So, in other words, these xi's are not adjacent to y. Otherwise, the I would be in J. So, xi is not adjacent to y. When we chose x and y, we chose them non-adjacent. So, xi qualifies together with y for being non-adjacent, with as many edges as possible. All right? Whoops. There. With degree sum as big as possible. So the xi cannot make this degree sum bigger. D of y is the same as before, so d of xi is no bigger than d of x, which is h. Yeah. So the degrees of all the little xi's they're all before h, including h. Okay. But how many elements are there in I? Well, h. H elements, right? One for every neighbor of x. For every neighbor of x, the vertex before that is, its index is in I. Right, so dh, let's look at the position, the hth position in the sequence. It might be this. So if everything here is green, if this is precisely this head big I, then that's the hth position. But it might be sort of earlier, like here. It might be at a green vertex, it might not be at a green vertex, I don't know. So, but the hth position is certainly not to the right of x, because there are at least h vertices up here, so the hth position occurs until before or when we hit x. Okay. So let me sort of put it here so that you don't think I'm claiming that the hth vertex is in is an xi. But then this is dh, right? So dh is the degree in that position. H was the degree of x. dh is whatever degree is here. So dh is at most h, right? Because it's one of these things, and all these degrees are at most h. But the d's satisfy star, so dn minus h is at least n minus h. Okay, so we have dn minus h here somewhere, and all these all these entries here are at least n minus h. And how many are there? There are h plus 1 many, not the same count as before. Right, so one of these vertices, call it z, is not adjacent to x because x has only h neighbors. So one of them is a non-neighbor. Then x, z are non-adjacent. But what's the degree sum? D of x plus d of z is at least h, that's degree of x, plus n minus h. That's whatever is the degree of z, it's going to be at least n minus h, and that's n. Which is bigger than this. Why? Because the degree of x and the degree of y correspond to I and j, and they both sit in this disjointly in this set of n minus 1 vertices there. Right? So I has d of x elements. Right? X has its degree neighbors, and the predecessors are all in I, and they're all different for different edges. So big I has d of x elements. Big J, that's just the neighbors of y. Big J has d of y elements. And all the neighbors of x and y are on this path. And they're disjoint, and they're a subset of this n minus 1 set. So their sum is at most n minus 1, and this sum is at least n, and that's a contradiction to this, which completes the proof. I think there's a lot in this theorem. And, I mean, for a start, nobody told Chvátal to think about Hamilton sequences. Right? So the quest was to find a necessary and sufficient condition, if possible, perhaps, or some weakening of that for the existence of a Hamilton cycle in a given graph. And there were some theorems proving sufficient or asserting sufficient conditions for the existence of a Hamilton cycle that involved degrees, like Dirac. And there was sort of 5 or 6 theorems following Dirac. So this somehow sums up what you can say about forcing Hamilton cycles just in terms of degrees. I mean, that's not a precise statement, but it's somehow the idea, I think, that made him think about just these degrees rather than the graphs themselves. That, yes. Okay. Yeah, that's a good theorem. Yes, of course, I haven't proved the other direction. So, proof of the forward implication by contraposition. So, we assume that the condition star fails for some given sequence. So once more, okay, let me write it down again. So given A1, AN, suppose star fails, what does that mean? It means there exists an I where this implication is not true, such that AI is at most I, but A n minus I is not large, is less than n minus I. Let's give it a name. Let H be such an I. So this I where this fails now has a name, it's little h, and we have to show that the sequence of little a's is not Hamiltonian, so we have to find a graph with degree sequence at least that is not Hamiltonian, just one. Okay, to show that is not Hamiltonian, we'll construct a G such that, okay, with degrees di bigger than ai for all I, not just for this particular one. That's no longer an I, that's now an H. With degrees big enough, but without a Hamilton cycle. Right, we just have to construct one whose degrees are big enough. Okay, so we don't know very much about this degree sequence. What do we know? Here's the sequence of little a's. Okay, and there's ai somewhere in position I. Sorry, no, I put those up there. So the entries of the sequence are above, I think. Used to be here. So ai is here somewhere in position I, and then we'll have position n minus I somewhere here. And we'll have a n minus I there. Sorry, h. This is now an h. Thank you for nearly telling me. N minus h, which we know is less than n minus h. So we would like it to be at least n minus h in order to make the sequence have property star, but it does not have property star, and the little h witnesses that. So that is what we know. That's all we know. There exists some h somewhere, some I, and we called it h, where ai is small, but a n minus I is not as big as a star would like it to be. So we now have to construct a graph that beats this sequence of a's by its degrees. But that's all we know. So we'll have to account for the worst case, that the a's are as big as possible given this. So let's assume that all these are as big as they can be, compatibly with this assumption that AH is H. So those have to be at most that. So let's make them all that small. So AH is at most H. Let's make all the smaller degrees also that big. Right? For all we know, that could be what we have to beat. And this one is not, this one is smaller than n minus h, so let's say at most n minus h minus 1. So let's give all these degree n minus h minus 1. And what can we do with these? Well, we know nothing about those. They can be big, but they can't be bigger than n minus 1 in a graph on n vertices. So this sequence here, lots of h's first, then lots of n minus h minus 1s first, the second, and then followed by n minus 1 entries all the way up. That's the largest possible sequence that's compatible with this assumption that star fails at position h. But we have to construct a graph that has degree sequence at least this in order to beat our unknown sequence, of which we only know that. Yeah, but that is easy. I mean, the graph is unique. Normally, graphs are not unique with a degree sequence. So here, let's take h vertices on the left. Let's take h vertices on the right. And let's fill up to n vertices below. We make this complete. So all these vertices are adjacent to everything there, adjacent to everything down here. All we need now is that there is a vertex left in here, and this is because h is less than half n. Right? Remember, condition star requires this for I less than half n. So if that fails, then there exists an I less than half n where this implication fails, and that we call that h. So h is less than half n. So these two h here are together less than n, so that exists. So why does this graph not have a Hamilton cycle? Because in order to pick up these h vertices here, the cycle has to come from the right. These are not adjacent here. So between any two of those, there's something here to which it goes, and then it has to come back immediately, because if it spent any time down there, then we'd waste another vertex up here before we can get across again. But we can't afford to spend more than h vertices to pick up these h vertices. So these h interim vertices between these must follow and precede these vertices immediately. Otherwise, we need more than h here. So we can't pick up these at all. And there exists one, and that's why there's no Hamilton cycle. Okay, questions?